Uh, Hello, everyone. Thank you for attending. I know it's late in Europe and holiday in New Zealand, but still, thank you for making it. And today we have Dr. Kostas he's a software development engineer at Technical House of Engineering. And today he'll be presenting about like seismic assessment and retrofit of reinforcement concrete using OpenSees. And thank you, Kostas, for taking time and presenting, and it's all yours now.
Thank you very much. Thank you for the invitation. I'm really happy that I can change some information with you in areas of common interest. And as you said, the title of the presentation is Seismic Assessment and Retrofit of Reinforced Concrete Columns using OpenSees. Actually, the first part of my presentation is about the seismic assessment of reinforced concrete columns. I would like to underline that the goal of my research is the seismic simulation of reinforced concrete columns for all possible failure modes. As you know, the static relationship between shear force and flexural moment in the span of a cantilever is identical to that of an actual frame member extending from the point of contraflexure to the fixed end support. The deformation mechanisms that are present in the column are shear, flexure, and pull out of slip of the reinforcement from the support or the lap splice. These mechanisms of behavior are considered to act in series, and they are considered additive, as you can see also in the figure. So what I'm going to present to you is each one of these mechanisms, how it can be modeled. As a basis, you can use also OpenSees for the basic analysis in some of them. And for the interaction of flexure shear, I will introduce you a fiber model that was developed and implemented in a standalone Windows software called Python. But I am planning also that to implement it also in OpenSees. So you can have an idea for the part of seismic assessment before I go to the part of seismic retrofit of reinforced concrete columns. So the pull-out slip, the development of yielding flexural moment in plastic hinges frame elements synonymous with yielding strain penetration in shear, span, and anchorage. Yield penetration destroys the interfacial bond between bar and concrete, as you can see in the figure. In the part of the reinforcement of the reinforcing bar in the shear span and the anchorage, where the strain is higher than the yielding strain, so the yield penetration length, we have a residual bond strength. In the presentation that follows, this part is considered, which is the plastic hinge length of the column, and is the only consistent notion of plastic hinge length considering the actual state of the reinforcement. So yield penetration, as I said, destroys the bond between bar and concrete, and it causes a reduction of column plastic rotation due to flexure, a reduction of strain development capacity of the reinforcement, and increase of bar pull-out contribution in the total column rotation. Now, how we can compute this yield penetration length and how we can define the pull-out slip of the reinforcement from the support. We use the basic equation that describe force transfer lengthwise from a bar to the surrounding concrete. A force equilibrium applied to an elementary bar segment length dx, as you can see in the figure, and a kinematic relationship, the slip of the bar as the difference of the developed strains by the two materials. So by solving this differential equation of bond through exact integration, we end up to closed form solutions that they describe the stress and strain state of the bar, and using simple constitutive material laws. So you can see a bilinear with hardening steel for the steel reinforcing bar, and a local bond slip law that has the bond strength and the residual bond strength. So this way of piecewise linear solution is helpful. Why? Because in comparison with the numerical solution, you have an fruitful inside of the design parameters that affect the plastic hinge length and the pull out of the reinforcement. So the tension stiffening model, and usually that one is introduced in also in OpenSees through the tensile behavior of concrete constitutive laws. In this case, I will show you how you can incorporate it directly through the differential equation of bond. So, as we said before, the moment shear relationship in the span of a cantilever and the horizontal loading is identical to that occurring over the length of the axial frame member, extending from the inflection point at mid-height to the fixed end support. According to the classic theory of flexure, reinforced concrete element is considered cracked when the moment exceeds the cracking moment. We consider discrete locations for the cracks, and the first crack, of course, appears at the critical section at the support in a cantilever column, and the transition from uncracked to cracked may cause a jump in strains in the moment tensile strain diagram of the critical section. So actually, between cracks, the real bus strains deviate from those defined from fractional analysis. So due to reinforcement slip, the degree of strain compatibility between steel and concrete in these locations is not well understood. So due to slip between the two materials, the plane section remain plane assumption is not valid anymore. So, and concrete cannot be considered as inert as would happen in a fully cracked tension zone. And we consider that it takes some length. This length is called the length of the disturbed region, where the compatibility between the two materials is satisfied. So we have zero slip. And so in this region between cracks, but after a length of the last crack, this disturbed region, we define the strain of the tensile bar of the column through the solution of the differential equation of bond, and the plane section assumption is not valid in this region. So for the anchorage, we use the solution by Tastan and Pantazopoulou, where describe the distribution of strain, slip, and bond for a bar that has yielded inside the anchorage. And for the shear span, we have the solutions from the differential equation of bond, but also the solution from the elastic response, where the plane section remain plane assumption is valid. And these two solutions should agree at the point of intersection by matching the slopes of the bar strain distributions, left due to bond and right due to elastic response, the matching of values, continuity, and compatibility of strains, zero slip at the start of the elastic response, as you can see in the figure. So the plastic hinges then is the length where we have the yield penetration length inside the shear span, inside the occurrence, where we have the residual bond strength, as you can see in the figure, and is triggered when the slip in the local bond slip law has a value greater as S2 in both regions. And having the plastic length, of course, we can calculate them in elastic column rotation capacity. So the algorithm I'm going to present to you defines the main flexural cracks of a cantilever column, the distributions inside the disturbed region for slip, strain, and bond, and it defines the plastic hinge length that is a useful value also for the analysis in OpenSees. And we use a standard section analysis with OpenSees, a moment curvature analysis that gives also the moment tensile strain diagram of a typical section given an axial load, and you can unify that in the same graph as you can see in the figure on the right. And we select a value of bar strain after crack formation at the support, and we solve for the length of the disturbed region emanating from the first crack. And having this length, we then have to decide where the second crack will be formed. We have to define that, and we check if this will happen inside the disturbed region where the equation of bond applies, or outside the region the disturbed region where we have the elastic response solution. After the formation of the second crack, we continue applying this procedure, defining a new disturbed region, and we calculate also distributions inside this region, and we repeat that until stabilization of cracking. That usually happens when the strain of the bar is close or less or equal to the yielding strain. In this procedure, we don't consider condensation of cracking. That means we don't consider secondary cracks after the formation of main cracks. And after stabilization of cracking, we define a total disturbed region, a region that starts from the support until the length of the disturbed region of the last crack. And inside this region, we continue we terminate the algorithm when the bar strain at the support becomes equal to the strain corresponding to the ultimate moment. After this point, from the moment strain diagram. So after this point, we calculate the distributions of strain, slip, and bond through the solution of the differential equation of bond. And we define the plastic hinge length, the hinge penetration length inside the shear span and in the anchorage. Now, I would like to show you a correlation with the experimental study where you can see how this captures the plastic hinge length and the rotation capacity of the column. You can see that this column is from the experimental study by Sachoglu and Ozebe in 1989. It's a square column with a shear span of 1,000 millimeters, 1 meter, and you can see the longitudinal reinforcement and the concrete and the steel strength. In the experiment, it had 5 to 6 flexural cracks, main cracks at yielding, and at ultimate, 3 times the yielding displacement. There you can see the damaged region and the plastic hinge length. The rotation capacity of this column was 3.5%. And the solution of the differential equation of bond in the algorithm that I already showed to you, based on a moment curvature analysis of the section of the column, you can see the distributions of strain in the occurrence and in the shear span for the second crack, third crack, and fourth crack. So we define four main cracks in the algorithm until stabilization of cracking. And you can see that at ultimate, we have a plastic hinge length of 632 millimeters. I would like to show you also, you can see here that this is a solution from the Flexure analysis with plane section assumption, and this is the differential equation of bond that comes is compatible with the elastic response in the elastic region of the column response. So you can see that inside the plastic hinge region, the plane section assumption gives lower strain values for the bar, and doesn't capture the the inelastic strains, the actual state of the bar inside the plastic hinge region. So now we compare this value of plastic hinge length with some empirical definition and fix the values of plastic hinge length that we exist in the Eurocode 8 part 3 in the famous equation by Professor Pisley. The classic definition where the plastic hinge length is the length where the moment exceeds the yielding moment, and the empirical definition that is half the depth of the section. Comparing these values, actually the problem with these values is that they are fixed. That means the inelastic region, as we know, spreads and evolves as the lateral displacements increase. In this case, they consider only the shear span and the yielding inside the footing, yielding penetration inside the footing, but do not consider the actual state of the reinforcement. So if we compare that to the experiment, if you can see that it's like the length is 520 millimeters. What the algorithm gives that they present to you is 632 millimeters. And you can see also with the colors what the other empirical equations give for the plastic hinge.
1 second, Kostas. Sorry to disturb. There are 5 values there and 4 equations. So can you explain that?
Actually, the equations are 4, but also the algorithm, this one is what the algorithm I present to you gives.
Okay.
And so this is the equation that comes from the yield penetration length from the solution of bond equation.
Okay.
And the other colors depending. Okay. Yes. And also we define also the slip of the bar pull out, and we calculate also the rotation that is 3.3% close to what also the experiment gave in this case. So this part of the presentation was about the pull out slip and the plastic hinge length. I will continue with the shear mechanism, flexural mechanism, and their interaction using a fiber beam column element. Actually, in OpenSees, there are various formulations for fiber beam column elements. I would like to present to you a proposal for a exact Timoshenko beam column element that takes into account shear flexure interaction, and is based on the modified compression field theory that was developed from the University of Toronto. And the beam column element is discretized in integration points, sections. You already know this. It is based in the discretization of the sections in layers fibers, where through appropriate constitutive laws, the forces of the section are determined. They are distributed in elasticity models that can be force or displacement based. I'm going to show you the case of the force-based element. And for flexural response, they are based on Euler-Bernoulli beam theory, and for to evaluate shear flexure interaction, they are based on Timoshenko beam theory. So the modified compression field theory, it is based on average stresses and strains and supplemented with local crack checks. There are 3 groups of equations: equilibrium equations, straight compatibility equations, and simple constitutive materials for steel and concrete. And based on this, a constitutive material for the fiber section of this element, a fiber model was based on this using this constitutive material. And as I told you, we saw now until now how tension stiffening effect and bond is incorporated through the differential equation of bond. In this case, in the modified compression field theory, is incorporated through the tensile behavior of concrete, and we can see that you can see here that the concrete tensile stress is assumed to decay from the tensile strength as principal strain increases. So this way the tension stiffening effect is incorporated in this case. And it's assumed that the average tensile concrete stress is transmitted across cracks, and this implies that stress in the reinforcement increases in proximity of cracks, but is limited by the yielding value. The fiber model, the biaxial constitutive law that is incorporated in the fiber model is an iterative procedure. It is based on the fact that we consider known the longitudinal strain of the fiber and the shear strain. The longitudinal strain comes from plane section assumption, and the shear strain has a parabolic shape along the height of the section, with the maximum value at the neutral axis of the section. And this procedure converges to the angle of the principal directions for stress and strain. In the transversal concrete stress, in this case, is calculated through equilibrium, considering a zero normal stress in the epsilon direction, in the y direction. And based on this biaxial constitutive material law, as section state determination, you can see here how the forces of the section are determined. We start from known strains, and we calculate the shear and the normal stress. We integrate those by summation of the contribution of each fiber. The shear force comes directly from integration of shear stresses. And since we are talking about a force-based element, we iterate in order to convert to the correct values of forces at the section. And just to know that we consider, as I said before, a parabolic shear strain distribution along section height with maximum value at the neutral axis. This is the solution for the anchorage in the footing, incorporated in this fiber model, and where it gives strain, slip, and ball distributions and the slip at the critical section of the column. So the capacity curve of this solution for the capacity curve of this for shear critical reinforced columns incorporated in this standalone software that we would like also to implement in OpenSees. It's a load control until process until shear failure until the maximum load, and then one more point defines the axial failure of the shear critical column. For each load step, for each force at the tip of the cantilever column, the displacements through from each deformation mechanism from slip, shear, and flexure is calculated and added together. The way this is done is for each step of shear force, we have the moment, shear, and axial load, and also for the step for each step of shear force and axial load, we have the moment, shear force, and axial load diagrams of the column, and we converge to the values to these values for each fiber section of the element, and we obtain the curvature, shear, strain, and longitudinal axial deformation. And based on this curvature, integrating these curvatures and the shear strains, we obtain the contribution, the displacement due to shear and due to flexure. And through at the critical section, through the slip of from the anchorage, we calculate the rigid body rotation of the column and also the displacement due to slip. We are adding those together, and we have for each load step, we have the corresponding displacement. And as I said, this is until maximum load, where we assume we have the shear failure, and then one more point is defined for the axial failure of the column, shear critical column, where we assume that the residual strength of the column is 20% of this maximum value. And regarding the drift at axial failure, in case we have a flexural response, actually also with OpenSees, you can analyze that under cyclic loading. You can define the axial deformation of the critical section, and multiplying that with the section height, you can have the axial elongation, and you can plot that versus the lateral displacement. You can see the response, and at the end you have the axial failure of the column. But what happens with shear critical columns? Then we adopted the equation of drift at axial failure from Professors Elwood and Mele, and how they define that is they define a shear crack of the column after shear failure, and the upper part of the column slides upon this crack, and by equilibrium of forces from the two parts, you can define the the displacement at axial failure. And so you have the full response of the cantilever column. And the angle of the shear crack is assumed 65 degrees. And now to correlate also this this fiber model and this process of defining the capacity curve with experimental results, we compare with the specimen one from Professors Sezen and Mele column test, and you can see here the equivalent cantilever and the experimental response. What OpenSees gives us Flexure monotonic response for this column without considering the interaction with shear, and what the shear strength models with degradation with ductility from the American one, the ASC SCI 41, and the Eurocode Part 3, the shear strength degradation measures and how they intersect with the flexural curve. You can see that for the Eurocode Part 8, the intersection is correct at the point where the shear failure is expected after yielding, and then we have the degradation of the column. This is the user interface of this Windows software. We gave the input of this specimen. You can see the response. You can see the contributions of its in each step of displacement. You can see the contributions of shear, slip, and accordant slip and flexure. And if you compare that to the experimental one, but also to what other softwares what OpenSees give, in case of course, OpenSees, I have considered only the flexure case. With gray, you can see the flexure response with a force-based fiber element in OpenSees. With blue, you can see what the famous program by University of Toronto incorporating modified compressor field theory and dual section analysis gives, and it captures the initial branch of the response. And you can see with the orange what Python gives. You can see that it captures the maximum load of, but it's more conservative regarding the displacements. And this is, we can examine why this happens. If we compare the contributions of shear, slip, and flexure at its level of displacement with experimental results. And we can see that at yielding, for example, the flexure is 60%, slip is 30%, and shear is 10% in the experiment. And you can see that it's a little bit more flexural response from the flexural contribution in Python. Slip is the same, and the shear is a bit underestimated. But overall, considering the complexity of this problem and how the different contributions are defined, we can say that this we can be satisfied with the comparison. And moreover, you can have through the differential equation of solution of differential equation of bonding anchorage, you have the contribution of strain, slip, and bond, and you can obtain the results and plot them to the the program you are you usually use for plotting for post processing. And moreover, moment curvature analysis and shear force, shear strain is obtained from a section analysis, also from this standalone software. And with this, I like to end the first part about seismic assessment, and you can download the Windows software from this link. And we are really hoping that we can have it soon also implemented in OpenSees, and have our tests also with OpenSees. If you have any questions, you can ask them now before I continue to the seismic part, to the part of seismic retrofit with FRPs, fiber reinforced polymer jackets.
Any questions, guys? Any questions? Any questions from people online? Okay, then I'll ask a couple of questions. Maybe. Do you have any?
Okay.
Yeah, go for it. Sorry, Roy.
Hi, Professor. I wonder if you can give more detail about the pattern windows of the wall.
Could you repeat? Not ask the
He's asking about more information about the Python Windows.
Yes,
software.
actually, it's a Windows tool. It's a Windows tool. It's free. You can download it and install it and make your analysis and test. It is available both in this link that I can show you here, but also there are other websites with freeware that you can also provided there. You can download it from the. It was developed during my PhD studies, and I used it for comparison with shear critical reinforced concrete columns. And the reason it was incorporated in the before incorporate not directly to OpenSees was because I wanted first to check some solution procedures, but also the element with the simple configuration of cantilever column and to correlate it with a large experimental column database that I had available during my studies, PhD studies.
Thank you. Is this software based on OpenSees, or is it?
No, it's a part. The code was developed independently, but the plan is to later to be incorporated over.
Okay, thank you very much.
Okay.
You're welcome. You're welcome.
Any other questions from anyone? Usually the questions slowly they creep in, so we need to ask like a couple of times.
Sorry, I have a question.
Yeah, go for it.
On slide 28, you compared your results with OpenSees. I was wondering what's the differences, what's the source of such a differences? 28, yeah. In
Here, right?
Yeah, exactly.
Yeah, I'm comparing with a flexural fiber model from OpenSees. OpenSees has also some ways to model shear flexure interaction, but I used only a flexure, the flexural response, force-based fiber model with Euler-Bernoulli theory that models only flexure. So the difference in the response is due to the fact that the column yields in flexure but fails in shear, and after the shear crack is formed, the degradation is brittle and sudden, and that's why it has the slope is you have this difference in the response between the two models.
Okay, you mean
the model and the experiment.
In the OpenSees, you didn't consider any limited state material model?
No, exactly. Not any zero length. The reason I did that, I want to show you that usually all the software is available for design. They don't have available. They have available only. They model only this flexural response. And I want to show also that even with a fiber model, the difference in this case of shear critical columns is very large, and you don't model the actual mode of failure of the column. This is the reason I did that.
Yeah, I got it. Thank you.
You're welcome.
Any other questions? Okay, so I
can continue to the.
I have a couple of questions. Just I'll ask like quickly. Maybe some are simple. Is this I mean, I assume you're using deformed bars in this, right? Is this applicable for plain bars as well?
Yes, actually, for plain bars, I can show you here. Let me go. Okay, can you see here the local bone slip law
Yes.
that I use for the deformed bars? In case of plain bars, you won't have a residual bone strength.
Okay.
So you change the constitutive law and you can incorporate, you can resolve the differential equation of bone.
Okay, cool. And the other one is like, how did you get the contribution from flexure shear from experiments? How did you calculate that?
Actually, that is reported in the paper of Professor Cezanne and Mele.
Okay.
I can imagine that curvatures can, from opposite sides of the column, can be measured, and then you can measure also the curvature. And the shear strain is with X linear transducers that they calculate also the shear strain, and you can define that also during the experiment. Sorry,
so it's not directly from experiments. After that, you use some equations to get from the strain.
No, I didn't do that. I used I can show you here. What I did, if you see the graph here, is taken from the paper, as is reported in the paper of this experimental study, and it's directly taken from their experimental results.
Okay. Yeah, I was curious how you got like.
Yeah. Actually, I'm telling you, the curvature is the shear strain. You have usually along the length of the column, you have transducers that you apply on the sides, but also in a X form,
Yes.
In this way you calculate shear strains and curvature.
Yeah. Okay. Yeah. And the other one is in the 28th slide again.
Yes.
So if this is for assessment, like seismic assessment, then we want to predict as per the Python, like it is, although it's predicting the strength correctly, the stiffness it's way stiffer compared to the actual experiments, right?
Exactly, yes.
So, I mean, if you're doing assessments, then you might actually want to go with the OpenSees one, which is the stiffness is there. And even if it's a little conservative with the capacity, that's fine, right? It's not too much. It's like maybe 10% off, I guess. But
the problem is for the post-peak response. This is the problem. But also the advantage from Python is that you have the contributions at each step. So you can make you can define the full response of a cantilever until shear failure.
But even in Python, it's the post-peak is not
the post-peak exactly. I couldn't capture it actually exactly. So I used one more point and a linear solution in the process, because in the way I calculate the capacity curve, can capture only until shear failure. This if you see also the modified compressive field theory and also response 2000, it gives you until the peak, until the peak response, you can obtain the curves. So that's why, since I was based on this constitutive law, I couldn't capture the post-peak response. But I used this a linear connection between the point at shear failure with the point at axial failure, and I wanted to approximize also this part.
Okay.
But the most important, the advantage that I told you is to capture the contributions of its deformation mechanism at each step of the analysis.
Okay. And one more thing is, like in OpenSees model, what materials and what reinforcement models did you use for OpenSees?
Yes, it's a Megalooikonomou and the Mander law for the concrete.
No, I mean in concrete O2, you mean, like which concrete?
Yes, and it's the Megalooikonomou.
Like which ones are they? I mean, I can't
it's
recollect.
Still yes. Actually, this I use the names of the professors who developed them, or the models, and not the, but it's still 0.1 and concrete 0.2.
So partly maybe that's why you are, it's not failing, or, okay, I see.
Actually, the only way to capture that is only to consider shear flexure interaction as in OpenSees with zero length elements and limit state materials that they are at the bottom. So this is the one way, or to add the shear mechanism in the use
wrapping aggregator.
Aggregator, exactly.
Okay. Yeah, I was about to ask next, did you try using the zero length section at the base and incorporate the bond?
Actually, I have tried that for some, but what I wanted to is sometimes the convergence and is not good with the zero length elements, and I wanted to calculate the whole response based on constitutive laws and integrate them and getting all the parameters. I succeeded in doing that until shear failure. For the post-peak response, actually is something that still needs research and development in order to capture it.
Okay. Cool. Thanks. I mean, that's all from me. Thank you.
Yeah, you're welcome. And I can continue with the. This is the second part is more OpenSees connected, and I can start the presentation. So the solution is the goal in this part is actually to retrofit substandard or shear critical reinforced concrete columns with FRP jacket. FRP jackets have been found to be beneficial for the compressive strength, shear strength, flexural strength, and displacement activity of reinforced concrete columns. What actually FRP jacket does is like when we apply axial load on concrete shortens and dilates. After this, with dilation, concrete can crack, and that activates the FRP and steel confining pressures and places concrete in triaxial stress state. That is beneficial, as I said, for compressive strength, shear strength, flexural strength, and displacement activity. So for low strain values, FRP and steel as a confining material behave the same. So they put an inward pressure as a reaction to the expansion of concrete, and that increases continuously. For now, thinking in terms of models for steel transverse steel confinement, where concrete is subject to constant lateral pressure. In case of FRP, the stress state of the stress strain curve describing the stress state of the section has to cross all active confinement curves up to a confined concrete axial stress strain curve that is associated with a lateral pressure magnitude equal to the tensile strength of the FRP jacket plus the yielding strength of ties. And you can see here, one moment. You can see here that you have one axial strain curve for its pressure, and by increasing that, you have a group of axial strain curves for its pressure, and the actual one that describes the FRP-confined-concrete behavior takes points depending on the level of axial strain from its and the level of the lateral pressure from these curves, defining the actual axial stress strain curve of FRP confined concrete. And so a model was developed for FRP and steel confined concrete in circular sections, and it's an iterative again procedure. You can see the response, the concrete axial stress, concrete axial strain response using zero tensile strength, and it's the cyclic behavior is based on Cancer and Yisa develop a model. And after imposing an axial strain on the section, a pressure coming from the FRP jacket is assumed. Then the Poisson coefficient until yielding of steel stirrups and the pressure coming from the steel ties is calculated based on the Braga model. This is confined concrete 01. And the confining pressure is in the concrete core is simply the summation of the lateral pressures contributed by the two confining systems, FRP and steel. And the Spoelstra and Monti model is basically used to define the remainder of the parameters, applying that model on the concrete core and concrete cover. Actually, what the advantage of this model is the following. You don't have to apply two different constitutive laws for the fibers in the concrete core and the cover, since it takes into account the different confinement states in an average sense. It takes into account that the concrete core is confined by FRP and steel, and the cover is confined only by FRP. You apply the FRPConfinedConcrete that's available also for both TCL and Python interpreter. You apply it in all the fibers of the circular section. So this is the command that is already available in OpenSees. It demands 19 parameters. Actually, I can mention them briefly. The material tag, the concrete core compressive strength, and concrete cover compressive strength. Actually, this is very useful in case you have a retrofit of a bridge pier or a circular column, where you repair also the reinforcement, and then you apply a new layer of cover at the column. Then you should consider the different compressive strengths for the old concrete inside in the core of the section, and at the new concrete you apply externally for the cover. Diameter of the circular section, dimension of concrete cover. You can consider here also partial FRP jacketing, so FRP strips with a spacing that are applied to the column, and the model has been correlated also with experimental results, and has been found also to model well also this case. Total thickness of FRP, rupture strain of the jacket, yielding strength of the longitudinal steel bars. This actually information is necessary because there is a failure criterion incorporated in this FRPConfinedConcrete that takes into account the interaction of buckled compressive steel longitudinal bars that interact with the FRP jacket, and they cause a premature failure of the FRP jacket. So this effect is modeled in FRPConfinedConcrete. And there is another failure criterion here that, as you know, for the FRP jacket, actually, when you test the tensile component of the FRP material, you obtain a much higher value of rupture strain of the FRP as the one when it's applied to a section of a column. And therefore, you should consider a reduction factor in order not to overestimate the overall response of concrete due to the confinement effect of FRP jacket. And a correlation, I provide here a correlation that is also one of these columns is provided in the OpenSees wiki page of FRPConfinedConcrete. You can download. It's the example. It's provided also for Python interpreter in the OpenSees PY page, and the correlation is for bridge piers that have 400 millimeters diameter and 1,350 millimeters effective height. There are two groups of specimens, A and B, where they have 3 specimens each. One is as built, the other 2 have a single or a double layer of carbon fiber reinforced polymer jacket. And the spacing is different in these 2 groups. The one group has steel reinforcement with 150, transversal reinforcement with spacing 150 millimeters, and the other has 300 millimeter spacing. The model in OpenSees, as I told you, you can download this model of this bridge pier, and get the response, is you apply FRPConfinedConcrete for all the fibers of the cover and the core of the circular section. A linear, the cantilever column was modeled by a linear beam element with the stiffness corresponding to flexural yielding, and a fiber element used to capture the flexural hysteretic behavior at the plastic hinge. The length of the fiber element was assumed to be half of the column's diameter, and a rotational spring at the bottom of the column represents the longitudinal bar pulled out from the footing. No P-delta effect was considered in the analysis. So you can see here the comparison with the specimens of this experimental study by Professor Kawashima from the from Tokyo Institute of Technology, and you can see that the comparison is quite good. These are the two specimens with carbon fiber reinforced polymer jacket for A groups, and the B group also. You can see more, further the correlation with experimental results. Now, this part was about the circular sections and the bridge space or circular reinforced concrete columns. And in case of rectangular sections, in circular sections, you have radial dilation and uniform stresses, confining stresses. In rectangular sections, the confinement is more efficient at the corners. You have non-uniform stresses, and there is the need for an analysis-oriented model where it can be easily applied and implemented in a software. We run a 3D finite element model with solid elements for concrete and cell elements for FRP jacket. It's a slice of a column, a square column under axial load. And we wanted to study how the non-uniformity of the stresses, of the confinement stresses inside the section. And you can see the plot of the stresses along the diagonals and along this parallel to the sides. And what what came out is that there are non-confined regions observed as usually this arching effect action is usually considered in confinement with steel ties. The concrete is subject to different levels of confinement. Near the perimeter, there is strong directionality, uniaxial confinement. And near the center, there is more uniformity, biaxial confinement. So we developed an iterative procedure, and after imposing an axial strain at the concrete rectangular or square concrete section, you assume a vertical stress. You calculate the volumetric strain and the area strain and side strain of the section. You calculate the diagonal confining force at the corners, and using a system of generalized springs, vertical and lateral, springs in parallel and springs in series. You can define the lateral pressures for each region and the vertical stress for each region, and you average that, and you get you converge to the right value after iterations of vertical stress. Then you have to check, of course, for the rupture of the FRP jacket, and we implement this procedure in OpenSees in a new version of uniaxial material that we would like to incorporate soon in the official version of OpenSees. The difference with the version already implemented is that there is a parameter section type in the command, where when it's circular C, the letter C, then it goes back to the old version, and when it's R, you can model the rectangular sections, and then you need to define the section depth, the section width, the radius of routing corners, concrete strength of existing reinforced concrete column, FRP jacket elastic modulus, FRP jacket total thickness, rupture strain of the FRP jacket from tensile coupons, and this reduction factor is always necessary as this is widely accepted in the experimental results of FRP jacket columns. And then we also, here is a comparison with square columns. It's an experimental study from Memon and Seik from the University of Toronto. And we compare, we applied a fiber model for the cantilever column, and we recorded the curvature at the critical section inside the plastic hinge length. And we compare the cyclic moment curvature response to the experimental one. You can see that although there is here, I should mention the fact that the curvature in the experiment there is a region that is measured, while in the fiber model it's a point of integration point as fiber section where are reported. So the difference in the response, a slight difference in the response, is also due to this fact. And you can see the comparison for different columns. They have, as you can see here, they have different levels of glass fiber reinforced polymer, and the axial load also is different between the specimens. And this is the last comparison. And I would like to conclude my talk with some conclusions for all of these parts of seismic assessment and seismic retrofit. For the, as I said, for the heel penetration, it occurs from the critical section towards both the shear span and the support of the columns. It is the nonlinear region of reinforcement, and pull-out slip is measured at the critical section, and it contributes to the pull-out rotation and column drift and column stiffness. And contrary to the fixed design values, the heel penetration length is actually the only consistent definition of the notion of plastic hinge length. We define the principal frictional cracking through the algorithm, proposed algorithm, the strength distribution in the disturbed region, and the extent of heel penetration, and the numerical results showed a good agreement with experimental evidence. Now, the Windows software, it has incorporated an exactly Mosemko beam model. It defines the distinct contributions, as we said, of different sources of column deformation: curvature, shear angle, axial elongation, and pull-out rotation. And regarding the FRPConfinedConcrete, the version already existing in OpenSees, and the one that will be incorporated for circular sections, and the one that will be incorporated in for rectangular sections. Regarding this for circular sections, it has no tensile strength, and has degraded linear unloading and reloading stiffness in the case of cycling loadings, based on the work of Casa and Yirsa professors. And the advantage of the modeling is that you apply a single constitutive law for all the fibers, concrete core and concrete cover, even if they are concrete core is confined with both FRP and steel, and concrete cover only with FRP. That is taken into account from the model, and you apply the single constitutive law. The comparison with experimental, the reverse concrete columns under cycle loading was from the experimental study of Professor Kawashima was good correlated. And regarding the case of FRP confined rectangular reinforced concrete columns, the arch action effect, which is widely accepted in the literature, oversimplifies the true nature of the state of confinement in the encased member. And we found that confining forces near the perimeter have strong directionality effects. And the model was implemented in OpenSees, and was correlate adequately to experimental findings. Now, future research priority, the main objective is to define an acceptable probability of collapse. We need to address the complexity regarding nonlinear softening response under large displacements and deformations that will contribute to acceptance of nonlinear response studies in professional practice. And the goal is, what I was also trying to do with this research, is to define shear and reinforcement pull-out in an ecosystem iterative formulation that will help minimize the non-convergent issues that arise with a large collection of zero-length nonlinear spring and plastic hinge elements currently used in nonlinear column response simulations. I would like to thank you for your attention, and the research was financially supported from the Alexander Onassis Public Benefit Foundation.
Okay. Cool. Thank you for the presentation. And any questions? Any questions from people online? No questions? Okay, then again I'll ask. Can you go to slide maybe 48 or something? 49?
48, 49. One moment, I put it in the
48. The experimental versus your model one.
Here, yes?
Yeah. So these, yeah. Can you go to the back one also?
Here, yes.
Yeah. But here, like the results in the south direction is like fine, but like at the front loading or what in the first quadrant, they were like not.
Yeah, the reason.
The experiments, right?
Yeah, the reason for that is in case of my modeling, the response is symmetric.
Of course.
As you can see in the experiment, it's not exactly symmetric, let's say.
Yes.
Probably this was due to the experimental setup.
Okay.
I mean, it is not the classic testing setup of a column under cyclic loading. So maybe this contributed to this effect.
Even in the next slide.
Yes. Again, it's symmetric, and
even
the other region also for yes. Sorry, yes, you can.
The other thing which I was like interested is like the hoops, like the cycle, the width of the hoops is also not matching, right? Like in the right side one, you have
in the right, yeah.
In the right.
This effect, you mean the effect that is going? Yeah, actually, the reason for that is that is the way the cracks are simulated. So cracks can be in the experiments. Cracks are not in the model. Cracks are open or closed, but in the experiment, cracks are partially closed, and this way of modeling makes the difference in the response. So in the cyclic behavior is the way the opening and the closing cracks is in the cycles is the way they are modeled. So this makes the difference.
And one more thing, I think it's also because of the material model for steel reinforcement what you're using. I think sometimes the shape looks familiar to me because some of my modeling, I get that shape and I'm not using the right steel material property, but I don't know in your case what you're using. But that's
I use the Megalooikonomou. You mean the parameters that calibrate the steel model? Yes, I use the same in all the specimens. Let's say.
Okay, so steel 01.
The Megalooikonomou, yes.
Okay, so probably it could be because of that. Maybe one of the reasons.
Yeah.
But okay.
But one other reason is I told you it's about how curvature is recorded, because imagine that when you define curvature in a length of the side of the column, right? But in the model, you have a point of integration. So this point corresponds to a specific moment.
Yes.
But in the experiment, the moment refers to a region that maybe is outside this where the point of or not exact to the point of integration you use in the fiber model. So this makes also the difference in the response.
Okay.
I don't know if you understood what
I mean, so, but the thing is, you're measuring the response, like the load displacement response at, let's say, top of the
this is not
column.
This is moment curvature.
Yeah, I mean, moment curvature, whatever, like maybe at the base or at a specific point, right? So
at a specific point, a specific fiber section integration point along the element.
Even for the experiments, you might be considering at a specific location, right?
But this is the problem, that you cannot measure in a specific location the curvature. You need a length of a side to capture that. So you are referred to a region, while in the model you refer to a point, and the region can have the moment may not be exact to the point you are considering in the fiber model.
Okay. Okay.
This is also contributing along with the other what you mentioned. It can be also parameters that affect the response.
I'm just thinking of things like, but okay, I'll again send an email if I have something else. But
you can all the participants, and also I'm available to answer any question regarding this material.
Cool. Any other questions from anyone? I have only that questions.
They were really useful questions, and thank you for all of you, and they were in the good direction to help the research also improve.
Can I ask one question?
Yeah, go for it.
Yeah, nice presentation. It's really interesting.
Thank you.
I'd like to ask you one question. Have you tried to combine the first part of your presentation with this one, for example, trying to model FRP along with the contribution of shear and shear slide, and I mean slide of bond?
Actually, I would like to tell you something about that. If you see the response of the as built column of this, for example, of the FRP, of the rectangular FRP, of the square FRP confined columns. If you see it without the FRP jacket, you will see a very brittle response because of the very poor spacing of the transverse reinforcement. And you can see now that after the FRP jacket, it changes the mode of failure, and it makes it like the shear failure, the shear dominant response is converted to flexural dominant response. In that case, you only need to model the effect of the confinement effect, and you don't need to model also the shear mechanism.
Okay, so you have ignored the shear contribution in the FRP model.
Okay.
If I'm correct, is it correct?
Is correct. Okay, regarding since you are mentioning it, I have not included here, but in case of circular sections, with this constitutive law, you can also define the shear deformations. I have not shown it here, but there is a paper I can send to you where it's described.
Okay, I see now.
But in the level in the material level, not
in the material level.
In the material level, you incorporate also the shear deformation. You define them, and you can the cyclic constitutive law also is reporting shear stress and shear deformations of.
Okay, so yeah, I joined the presentation late, so I didn't follow the first part. I only attended partially. In the first part, does your model is available in the form of a uniaxial material in OpenSees, or?
Yes, FRPConfinedConcrete is available in both.
The first one that you include all the contribution of shear and
No,
slide.
only for now, unfortunately, it's only available as a standalone Windows software that you can. It's a simple application. You can install it and run it on your PC.
Okay, so which means that that model is not going to be useful. For example, when we want to capture the shear and the shear contribution and slide in a certain component in a building or in a structure, right?
Yeah.
For now.
Okay. For now, exactly. For now,
Yeah.
it's only to test. You can test a cantilever column or a double curvature column, and you can define the response for that, and maybe use this information to make your analysis in OpenSees by putting the correct parameters in some hysteretic models or other materials you have in mind for analyzing the whole structure. Yeah.
Good. Thank you. Wish you the best.
You're welcome. Yes. Thank you very much.
Any other questions? I mean, they do come slowly, so.
Yeah, it was a time a little bit difficult.
No, they usually like everyone is waiting for others to ask, and then they like.
I see.
Like they keep coming. So, guys, any other questions? Or good to go? Okay, looks like no other questions. Cool. So, I mean, I think no other questions. If at all you have any other questions, please feel free to email Kostas. Like, I think he will be happy to take them.
Really happy, and I'm eager to answer all the questions regarding this presentation or other papers that you have that are related to this research.
Awesome. Thank you, Kostas, for the presentation. We really appreciate your time, and
thank you for the invitation.
Really, and hopefully it will help a lot of other people who will be trying to use this. So yeah. So
thank you very much for the invitation and to give me this opportunity to present some results of my research. Yes.
Yeah, and just for the next presentation, we will have it in 3 weeks because